All right, so section 8.4, like I said, we already started talking about, we did the multiplying, we did the simplifying piece, but today is going to be divide. So the one extra piece to pay attention to is not only will we have restrictions on the domain immediately, but once we flip that second fraction, the one that we're going to divide by, and it is just what we did yesterday, but that added piece. So did that.
It's never restricted. Wow. That's a lot of experience.
To divide, multiply by the reciprocal. So like I said, it's not really any new math. It's just that we have to pay that extra special attention to, hey, wait a minute, I've got a couple of new restrictions because I flipped this fraction. So it's like every step that you take when you do this, you're thinking, okay, domain, in the back of my mind, domain, do I have to add any new restrictions to the domain because of the math that I'm doing? So this says, what is the quotient of, and the first thing I see is this 2 minus x. And we talked yesterday about how we're going to need to reverse that. I mean, we know that when we go through this process. So we've got our 2 minus x, and we're going to pull out a negative 1 to make that x minus 2. And notice we're going to factor right away, because we have to talk about restrictions on the domain. We need to see where those zeros are. And then down on the bottom we have x squared plus 2x plus 1. And no greatest common factor, but yeah, that's a perfect square trinomial, because this is x squared and this is 1 squared, and 1 times x doubled is 2. But we talked about this yesterday. We really probably just want to see this as x plus 1 times x plus 1 at this stage in the game anyway, because we're going to want to see what we go ahead and cancel out. And then we're going to divide by, well, x squared plus 3x minus 10, no greatest common factor, not a perfect square trinomial. Good old-fashioned factoring it is. What are they, everybody? 5 and negative 2. And then x squared minus 1, one of our little favorites there. That's our difference, 2 squares. All right, so we start right now with domain restrictions, because this is the first chance we have to see everything in factored form, and that means we have a chance to say, okay, these would be my zeros. Where would they be? So far, that's what we have.
Add away, Eli.
You got it. Now, the first fraction is going to stay exactly as it is. Not doing anything to that. But now it's flipping time. We need to flip that second fraction because we have to multiply by the reciprocal. So we're going to change that to a dot for multiply. And flip it. And then we stop, because we now have a couple of restrictions on the domain. What other numbers can we not use in this?
2 and
They're out. Now, if we did everything right, those should be the only restrictions on the domain. After this, our answers should come from what we have right here. Occasionally, if you didn't factor out the greatest common factor, you might find another one later on, but this should do it. So, are you canceling like crazy? Stuck there? That's it? So, don't lose your negative 1 out in front here. That's still part of our answer, but we won't put the 1 down this time. We'll just do the negative. And then x minus 1, because it's always top times top, bottom times bottom with fractions. And then we have an x plus 1 and x plus 5 in our denominator right there. Second parenthesis. Any new restrictions on the domain? No, like I said, because if we're doing top times top, bottom times bottom, we've already dealt with everything that's going to show up in the denominators. We've got all that taken care of. But there it is. Isn't that beautiful? All right. These look like a couple of monsters. Nah? No challenge. What is the quotient? X squared plus 5x plus 4. I'm not going to read that whole thing off. In simplest form, state any restrictions on the variables. So let's get started. No greatest common factor could be a perfect square something. It's not though, right? Because this would be x squared and 2 squared and 2 times x doubled is 4x. So what'd you get?
X plus 4, x plus
Same thing down here for your denominator, nothing fancy about it. What'd you get?
x plus 4, x minus
Keep it division, because we have to be able to see the restrictions in the domain. X squared minus 1, what does that factor into?
plus 1,
Ooh, 2x squared minus 6x. What do you do with that? 2 and an x. Like so. Restrictions on the domain. What? And 0, good. Yeah, wherever there's an x, we have to be concerned with that. And this is the one right here that sometimes people will miss. If that's a 0, our denominator is going to be 0. What do we do next? Flip. Then what? New restrictions on the domain. They are. Then what? Console. Oh yeah. Lots of that. What's left? 2x on the top, that's it. Bottom. That's it. Any new restrictions on the domain? We did our job right. Done. That's a pretty one. Some good stuff there. B says, let's not actually do this problem. Without doing the calculations, what would be the greatest number of restrictions on the domain? With that little monster there. How many?
1, 2, 3, 4, 5, 6.
That seems like a lot of restrictions on the domain. Where are they coming from? 2 here, 2 here, and
the top.
Those are quadratics. We should have 2 zeros for each one of those. And when we have to flip, now we're going to have a new denominator in the second one. So we will have 6 total. Unless one of them's a repeat, you know. And that could happen in something like this. But they wanted to say, without doing the calculations, you know, best guess, what's the greatest number you could have? Well, it's not even a guess. It's calculated that there would be 2 for each one of these. And those would be our zeros. So 6 total. All right, now, those were fun problems. Things get a little hairy on this. It's a word problem, and it's at the end of a section. So we know things might get a little more difficult here. This says, your community is building a park. It wants to fence in a play space for toddlers. It wants the maximum area for a given amount of fencing. That makes total sense. You want the biggest space possible, but you have, you know, X number of dollars to buy the fencing. So you start with, hey, this is what we have money for. How can we make this work? And it says which shape, a circle or a square, would provide a more efficient use of fencing, which means cost-wise, which one would give you more area for the fencing that you have. So one measure of efficiency is the ratio of area fenced to fencing used. Oh goodness. Or area to perimeter. Which of the two shapes has the greater ratio? So here's what they want us to look at. Area to perimeter. The problem is we have a lot of variable stuff going on. And gonna have to figure out how to get perimeter and area in a unit that makes sense for both of them at one time. So when I look at what's going on with the square, I start thinking, okay, I need to know the area, and I need to know what's going on with the perimeter. And pretty obviously, there are no p's in the area formula. So I want to figure out, well, what can I do that would get me what I need? So I start with this. P equals 4s. And I say to myself, self, there's an s in that area formula. So if I could get this solved for s, I would have something I could substitute into that area formula. Perimeter divided by 4 equals a side length. That makes total sense. This is a square. Perimeter divided by 4 equals a side length. And I want to see what happens with that in the area formula. So that's exactly what I have to do. I have to take p over 4 and put it in my area formula. So p over 4 squared equals my area. Well, let's see. We can do a little math there. That's going to give us p squared over 16. Now, they told us what we want to do is compare area to perimeter. Overall, that's what we're supposed to do. So let's see. Area is right here. That's our area. And now what we have to do is compare that to the perimeter, which is just p. But the whole reason that we put a p into the area formula was so that we wouldn't have s's and p when we were looking at this. We want to know, comparatively, how does this work? And to do that, you need one unit to compare it to. Wow, that looks really weird, because we don't divide fractions. What do we do? Well, that's kind of good news. So what's going to happen? One of the p's will cancel. Just one. So for this one, it's perimeter divided by 16, which, because they want me to compare that to something, I really want to think of that as 1/16 of the perimeter. So that'll give me something to compare to. And now what I have to figure out is, well, what does the other formula do to the perimeter? And the other formula happens to be a circle. So you could argue circles don't have a perimeter, Cedarholm. Yeah, it is the circumference, right. It just has a different name. But if we want to keep this in two units that we can compare, we're going to use P for circumference. We know that that's, perimeter of a circle. So perimeter will be used instead of circumference for this. All right, so I'm starting here, just like I did with the last one. Let me change colors. I probably shouldn't do that in the same color. Now we need to think. We want P in the area formula. We're going to have to substitute for something so we can get P's into the area formula. What do we need to solve for? Yeah, we got to solve for R. So there's our R. Now think about what we did before. What do we need to do with that? Plug it into the area formula. Well, we can square that. It'll look a little weird, but we can do it. Not because of the p squared. It's not going to look weird because of the p squared or because 2 squared is 4, but this is the part that's going to look weird. Pi squared. But we don't have to deal with it very long, right? What do you see? One of the pi's is going to cancel out. we supposed to compare this to again? The perimeter. Okay, so we've got this p squared over 4 pi, and we have to compare that to the perimeter. Come on. What do we do? It's definitely not simplified yet. Is that pretty good news? A little bit. I'm supposed to compare these two. I have this one as 1/16 p. This one's going to look kind of weird again. Notice they both have the perimeter formula. So if we want to know which one of these is going to give us the most effective use, we need to know which one of these is bigger. 1/16 or 1 over 4 pi. I would probably want to see that as a decimal so we can know which one of them is going to be a more effective use. So we've got 1/16. And then we have 1 divided by another set of parentheses here, 4 times pi. And I'm actually going to use the nice little pi button. It is the caret symbol for powers, second caret symbol. Which one's bigger? That's the circle one. Circle is more effective. Okay, so why don't we see all kinds of kids' playgrounds around the United States that are made with circles? You ever seen a city lot that's in a circle shape? Oh, so most people would say, oh, let's just buy a little more fencing and make a rectangle out of this or make a square out of this. But if you had X number of dollars and that was all people are willing to spend, you really should be making a circle. You should, compared to a square anyway. Because our got it down here says, how about an equilateral triangle? How about that? Well, now it gets interesting. Look at that wonderful formula for the area of an equilateral triangle. Woohoo!
I'll see you guys tomorrow.
What do you know about equilateral triangles? Tell me what you know about them.
Equal.
What's equal?
The side one.
All the sides. Good. You just gave me a formula to use. You just told me the perimeter equals 3 times the length of the side. If all the sides are the same, then that's the perimeter. So what do you suppose we should do with that? Solve it for S. Why do we do that?
We're going to plug it into something.
We sure are. We're going to plug it into this obnoxious mess right here. Area equals 1/2. Here's our S. You know what? Let's simplify this formula first. I can't stand the way they wrote that. That's not the way that you guys learn the formula for equilateral triangle in geometry either. So here's what we're going to do. We're going to make everything there a fraction, and then we're going to multiply top times top times top, bottom times bottom times bottom. So 1/2 S over 1, square root of 3 over 2, S over 1. Otherwise, this is going to be a major mess. Across the top, we've got a square root of 3s squared. And on the bottom, we have a 4. That's the shortcut formula we teach in geometry for the area of an equilateral triangle. Square root of 3 over 4 side squared. Now it's going to be easy to work with. So now we take our obnoxious little p over 3, slap it in here. Like so. What's What's next? Square it. Okay, so p squared over 9. All right. Well, let's see. That'll be the square. Well, we want to write this to make this easier. I guess p squared over 36. That wouldn't be too bad, I suppose. We done? What are we supposed to compare this to? Perimeter. Yeah, because right now you should be worried. Hey, there's a p squared in there. There wasn't a p squared in the other ones we did because we're not done. Or we do that. We're staring at it and hoping it goes away. It's still there. Multiply by the reciprocal. Square root of 3 over 36, p squared. We could keep that p squared in the numerator for just a second to help us out. What's happening? 1p is gone. That is good news. So now we have the square root of 3 over 36 p. Is that better than a circle? Well, let's see. Square root 30 divided by 36. Oops, I better finish off those parentheses there. There we go. There. Better than a circle? 0.04? No. So that's what they wanted, was they didn't want to know which one of these overall would be best. We would tell them circle. They wanted to know, is this better than a square? No, a square would be better than this. So, equilateral triangle would not be a good way to go. Square would be okay, but circle would be better. I mean, we could compare all three of them and go that way. So square is better than this. Hate to tell you, the whole reason we do that one, ACTs. ACTs usually have something like this where they want you to compare those pieces together. This is over and above what we're going to have you do as you go through the homework, but ACTs, that's kind of where it goes. So 43210, me, how do you feel about our dividing rational expressions? Yeah, that last one kind of scared some of you a little
Like
bit,
a
huh?
2.
Yeah,
The
that last
three
problem was
minus the
scary.
last two.
I know, I
4
know.
minus the last 2.
And that is, like I said, that's the wonderful ACTs right there.
Wonderful.
Literally, they do. They have those problems that say,
Fun
which would be the more effective use of fencing, you know, as you go through it.
6, 9,
5,
6, 9, 15, 14.
12.
Ooh, I better see if we can do all of those.
Yeah, I think we should do 21.
I think we can only do 20, 25.
I mean, I already have homework. Other stuff.
Well, yeah, you've been gone.
Yeah, that's why I didn't want to leave today.
We
Otherwise I would be here right now. I would not be here right now. We could try it
Oh,
out.
fun problems.
A lot of canceling.
729, a lot of canceling. All right. Let's take those
Oh
off.
my god.
Yeah.
I'll leave all the fun canceling, but take off some of the, in fact, those last few are just adding fractions, adding and subtracting fractions, which is kind of silly, but
Thank you.
we'll take those off.
Yes!
All these things. There we go.
For your help. Sincere. So it goes right on there.
I can maybe comb this out.